Let's continue our look at Kerberos, the authentication protocol used by directory services. Kerberos is named Kerberos because it's based on the three heads. Kerberos, of course, is the mythological creature that had three heads, and it was a dog that guarded the gates of hell. And in this case, the three heads of the authentication protocol include the KDC, that's the Key Distribution Center. In implementation, that is a domain controller in Windows Active Directory. The second head is the principal, the authenticated user. That's the consumer of resources. And the third head is the principal that is the resource itself. In this case, we're talking about, for example, a file and printer sharing service. So these would be the three heads that are represented by Kerberos. The KDC is the trusted component. That's the source of the trust. And it establishes this security boundary, this realm of trusted principals. Those are users and resources, or primarily the nature of the principals we're interested in. A user will authenticate to the KDC and then is trusted by the KDC. The resource server on boot up authenticates to the KDC and then is trusted by the KDC. They are issued Kerberos tickets, and the Kerberos ticket has two halves. The ticket includes proof of authentication as defined by the KDC. So the KDC builds this ticket, and he validates the authentication of the user and then encrypts that validation in half the ticket. And in the other half of the ticket, he encrypts the authentication of the other principal. And in this example, we're talking about the file and printer sharing service on that resource server over to the right. And when the user then wants to access that resource server, he uses this Kerberos ticket, feeds it over to the resource server. The resource server validates that the ticket actually came from a trusted KDC, and then goes and decrypts the side of the ticket that includes the user's credentials as defined by the KDC. And now the resource server trusts that the user's identity has been validated by the KDC. And if the KDC believes this is that user, the resource server trusts that it is also that user. At the same time, the principal, when it receives the Kerberos ticket, says that if the KDC trusts that that's really our trusted resource server, then the user also has trust that he's communicating with the right resource server. And so based on this level of trust for the KDC and the two halves of the Kerberos ticket, the principals now authenticate to each other and have trust that they're communicating with the appropriate other endpoint for this access to the resources. So Kerberos is referred to as a single sign-on technology. Again, the point is of single sign-on is that the user needs to authenticate one time, the time that he logs on to the Kerberos KDC, and at that point he's given a getting ticket. Using that as his access token, he now can use that getting ticket to access any resource enterprise-wide for the duration of that ticket. Typically, this TGT, as it's called, a ticket getting ticket or a ticket granting ticket, this TGT is good for about 10 hours by default. That would be about the time of a workday, a typical workday. You get in a few minutes early, you work an 8-hour day, you take an hour for lunch, you work a few minutes late, you're at about 10 hours. So that's the single sign-on component of Kerberos, is that we log on once to the KDC, we get our TGT, and using that TGT, we are now able to authenticate to any other resource enterprise-wide. And what is this enterprise-wide? Well, that is the basis called the realm. That's the boundary that defines trusted objects. Anything within the realm with the same namespace, like boboville.com, is trusted by and trusting of every other object with that same namespace. First, we have this logical namespace that defines this logical boundary of trust. But then in implementation, we use software controls to limit access based on that namespace or that level of trust. So the realm is this boundary defined by namespace, but implemented and enforced by software. And again, we talked about the common namespace. It is a domain and a top-level domain affiliation. And then each object, each principal will have additional namespace, perhaps by the OU, and additionally username and or local host name, for example. Objects, again, within this realm can trust and be trusted by other objects within the realm. Between realms, you can build trusts to extend this trusted environment. So we use external trust between these realms or domains, as Microsoft calls them, and we can extend the trusted environment, the trusted computing environment. Now we're looking at remote access services that also are commonly incorporated in this directory services environment, because very often we have telecommuting users. Very often we have administrators that don't want to have to go to the other building or fly across the country to modify the configuration of some server. And we also have wireless users that also run through this same remote access user configuration or implementation. And because these users don't have to physically be within the building and physically connect to wires that are only available inside the building, we don't have as much trust for who those people are. So we therefore will more strongly authenticate those remote users. And that's where radius, TACACS, and diameter come into play. Radius is remote authentication, dial-in user services. That's the open standard. Cisco took that open standard of radius and implemented it in a Cisco environment. They call this TACACS, or Terminal Access Controller Access Control Services. And the new generation of these remote access services is diameter. This is the latest and greatest. And again, diameter comes to us as a play on words. It's the second generation of radius. It's twice as good as radius. So 2 times radius equals diameter is the notion as to where they came up with this name. Now, these authentication services are referred to as AAA services. They include authentication, authorization, and accounting. But today, we don't need the accounting part of it. Today, we need auditing or accountability. So we do logging of the actions that these users who have authenticated and have been authorized are performing. What exactly did that guy do? I want a record of it, just in case there was something bad or some mistake occurred. And again, this is all an extension of the original point-to-point protocol, a dial-up service protocol used originally by telephone and modems attached to our computers. And originally, we were dialing up bulletin boards. So we'd have a client with an acoustic coupler over a telephone line to a bulletin board that was another server with an acoustic coupler. And again, this point-to-point protocol, this dial-in service, extends to wireless and VPN services and will soon be used in the cellular environment in the 4G networks. We'll take a quick break here and we'll pick up where we left off. Continuing our lessons on remote access services, we're going to look at diameter. Diameter is the newest generation of these AAA services. Remember, AAA is authentication, authorization, and originally it was accounting, but today more so it's auditing or accountability, keeping track of what the user has done. But diameter is the new kid on the block, and it's the next generation of radius. They get the name playfully from diameter being twice as good as radius. 2 times radius equals diameter. The diameter protocol is that same AAA service, but it has improvements in many, many categories, many areas of the AAA support that radius and TACACS provided. However, the primary area of support is aiming at 4G cellular. Now, today many of us have cell phones that imply that they are 4G capable. The kicker is there isn't any such thing as 4G today. There's 4G long-term evolution, LTE. That is a tiny step, perhaps not even 10% of the way between 3G and true 4G cellular. True 4G cellular has many requirements that our cellular systems today cannot support. So true 4G does not exist today. It's 4G LTE. Diameter is one of the protocols that is going to be used to support the services that true 4G is going to require on our cell phones. Now, one of the primary issues with 4G is that your cellular connection and your data flow connection will be as good as if you were attached using a hard wire to a network. In other words, you always will be able to get a signal and you will always have a high data rate of connectivity using that signal. Now, what we know is with your cell phone today, you will always find dead spots here and there throughout the local community, and especially as you travel to more remote locations, you get worse and worse connectivity. In other words, you might not get a signal, and if you do get a signal, you're going to get very slow data throughput because the connection is really weak. Well, that's not satisfactory with 4G cellular. One of the techniques they're going to implement with 4G cellular is that on your cell phone, no matter who you pay as your cellular carrier, and today those carriers include AT&T and Verizon and others along these lines, those are the carriers. No matter who you pay, all the carriers must support your connection. So if, let's say, you're an AT&T customer with your cell phone, that's who you pay your bill to, and in the diagram here on the slide, we're going to say that cellular carrier A, the blue tower, is AT&T. So while you're close to that blue tower, you're going to get a good strong signal and you're going to get a good data rate when we get to 4G. However, as you move from the area around the blue tower to the area around the red tower labeled cellular carrier B, that would be the competition of AT&T, like Verizon, for example. As you move away from carrier A towards carrier B, your signal is going to degrade from carrier A. However, when the signal from a carrier that you don't pay any money to, when that signal gets stronger than your carrier A signal, carrier B has to carry your connection, in spite of the fact that they're not being paid by you in any way, shape, or form. And this is one of the components of 4G cellular that has yet to be ironed out. However, this is the area where Diameter, a protocol that will support transferring your connection from your carrier when you're near the blue guy, as you move towards the carrier B away from the blue guy, Diameter will transfer your authentication information, your credentials, from carrier A to carrier B so that carrier B can continue to support you with the strongest signal that you have available to your cell phone, in spite of the fact that it isn't even the carrier you pay. That's a pretty amazing thing, and I don't know exactly when this is going to sort itself out. That's why we're not at 4G yet. But when we do get to 4G and we get those agreements ironed out between the different carriers, that no matter who you pay, the carrier that provides you the strongest signal must carry your connection. When we get to the point where that detail is ironed out, we have the protocol to transfer your credentials from carrier A to carrier B and maintain that connection and that high data rate, maintain your session with whatever your services are, whatever you're accessing, whether it's internet, whether it's local resources on your corporate enterprise network, et cetera, but the Diameter protocol will keep your credentials and your sessions intact as you transfer from one carrier to another. So this is a review of the remote access protocol Diameter, also called a AAA service, and Diameter is the new generation that is replacing Radius and TACAX. We'll take a break here and we'll pick up with the next lesson. Picking up where we left off, we're going to look at a diagram that shows the implementation of Radius and TACAX. These implementations are very similar. One is the open standard Radius. The other is the implementation of Radius by Cisco. So Radius and TACAX are approximately the same service. Now, in this example, we have a user on the lower left, and that user is using some sort of remote connection. And that remote connection started out in the old days as dial-in over analog telephone lines. But today, these services using the point-to-point protocol has been extended to virtual private networks and to wireless systems, wireless network connectivity. So that remote user could be one of those three types of users connecting into the corporate networking environment. And they would connect into the network access server, and this is the guy that He might be a VPN concentrator. He might be an old radius server that has the modems attached to it with telephone lines. Or this might be a series of access points that are managed by a wireless access controller. And that would be the nature of this network access server, depending on the nature of the clients that this environment is supporting. In most cases, this remote user would establish the connection to the NAS server, network access server, and that network access server would allow communications only for the purpose of authentication. Any other request would be denied. If you notice, there is the switch between the NAS server and the resources on the LAN, and that switch is currently open because until that client authenticates, that's the only thing the client can use this system for, authentication. So the client would connect up to the NAS server would prompt the client for authentication. And that authentication might be based on the radius server or the TACAC server, that's that middle server on the top there. And that system typically will support its own independent user database, or that system might backend into a directory services database for authentication services. If we're in that corporate environment, we have directory services, let's use that bigger database. It may simplify some of our needs. However, if I don't want all my users to be able to dial in, maybe I just want a smaller database, more isolated, more localized, if you will. In that case, I'll use that local user database on the radius server itself. So that back end there behind the NAS server for authentication could be one or more servers that provide that authentication service. Now, if the user successfully authenticates, the authentication server notifies the network access server that this guy is now authenticated and he's allowed to do these things. And at that point, the network access server closes that switch. By the way, this is a logical switch in this example. I've diagrammed it here physically, but it is a logical switch there. And only when the user is authenticated and authorized to access resources on the LAN would the NAS server allow that user to make the connection into the resource servers. And so that's what this guy does. Moving on, we'll take a look at virtual private networks. Now, this is one of those supported remote access services, VPNs. Basically, what the VPN typically does is isolate the communications that are flowing through the VPN from the network that the VPN or that this communications are flowing through. So we have some form of isolation, encapsulation, that make these communications virtually private because of this isolation from the networking environment that these communications are flowing through. Most of the time, the VPN implies an encrypted channel because very often what we're trying to accomplish with this isolation is to keep the information confidential. The best way we have to keep information confidential as it flows across a network is by encrypting all the information. So typically a VPN implies that we are encrypting all this information so that it is non-readable in case somebody's sniffing those wires and able to capture that packet, if you will. And if we encrypt it, it makes it unreadable. That's our primary implementation. However, VPN does not exactly mean encryption. We have other forms of isolation. I might encapsulate a layer 3 protocol in a layer 2 frame so that I can send that IP packet through ATM network or frame relay, for example. And so this is also a form of VPN. These are the two ways that we see VPNs used, either encapsulation and not encrypted or encrypted. We see a list of VPN technologies on the side. We see Secure Shell. That was one of the earliest implementations of a secure channel. Now, it originally was not designed as a VPN. It wasn't really for, let's say, file transfers, for example, or the flow of sensitive data. It was really designed for securing the remote administration of servers. It replaced Telnet. Telnet was one of the early protocols used on IP networks so that an administrator could remote access into a server and reconfigure that server as necessary without having to get up and sit at the keyboard and a monitor in front of that server. So he could do it from his workstation using Telnet instead of having to walk down the hallway and sitting in front of the server. The problem with Telnet, though, is everything is in plain text. So if there is any bad guy in the environment who might be capturing the information flow across that network, the bad guy could actually steal that information and perhaps even use that information to reconfigure the server himself in an unauthorized fashion. So they figured out that Telnet was non-secure. Let's encrypt those communications because this is kind of sensitive information. So they invented the secure shell as an encrypted channel for remote administration. That was its primary use. Today it's evolving into more of a VPN. We have the point-to-point tunneling protocol, PPTP. Now this was produced as a joint venture between Microsoft and Cisco. And this guy originally used RC4, the encryption algorithm, to encrypt the payload. So Secure Shell was an asymmetric algorithm. Point-to-point tunneling protocol used RC4, which is a symmetric key encryption algorithm. These two guys encrypted data as it flowed across the network. L2TP is an encapsulating protocol but does not provide encryption. So there's no confidentiality services with Layer 2 tunneling protocol. L2TP is another Cisco proprietary technology but is also now being used by Microsoft. IPsec, because the Internet Protocol has no security services built in, if you needed to run security services over an IP network, IPsec, IP security is your primary tool. This guy encrypts information over IP networks and is a classic and probably the most heavily utilized VPN technology today. Now the next one down, SSL, Secure Sockets Layer, is a little bit different from a VPN. See, a VPN implies we have known and trusted endpoints, like within the Kerberos realm, whereas SSL says I can be used in an environment where the users are essentially anonymous, but I can still secure the communications channel. So SSL is used heavily on the public internet, where we have anonymous users that are accessing resources up on servers, and without having to know who that user is, we can implement a secure channel, SSL channel, and encrypt all the information that flows back and forth. So that's where SSL came from. However, it is being used today more and more as a VPN technology. And that extends to the newer version of SSL called TLS, the Transport Layer Security. So TSL is an enhancement, if you will, to SSL. Finally, the implementation of SSL as a VPN, it is now being implemented as Secure Sockets Tunneling Protocol, SSTP. So these are all VPN technologies that either encrypt or encapsulate without encryption the information flowing from one node to another node on a network. We'll stop here and pick up where we left off. This lesson covers network address translation called NAT and its close relative, port address translation, PAT. Now, NAT was invented, NAT and PAT, by the way, jointly, were invented to extend the lifetime of IP version 4. IP version 4 uses a 32-bit IP address with a handful of those addresses allocated to the public address space used on the internet. Problem is, those public addresses were consumed very quickly and we started to run out of public IP addresses. So NAT and PAT were invented to help extend the lifetime of IPv4 by sharing one or more public IP addresses amongst perhaps hundreds or even thousands of users on the public internet. So instead of needing hundreds or thousands of public IP addresses, they all can share one or two public IP addresses, minimizing the need for so many public IP addresses and extending the availability of those public IP addresses. Now, NAT and PAT are typically configured on the external firewall. This would be the firewall that isolates your privately owned enterprise network from the public internet. Firewall, of course, is a security device that provides isolation as a security boundary between these networks of differing trust levels. We have more trusted environment behind the firewall on the private side and less trust for that network environment outside on the public side of that firewall. So NAT is configured on that external firewall where we have this boundary between public and private. And again, it's all about sharing these public IP addresses, making them much more usable and much more shareable. In addition to this extension of life for IPv4 and the more efficient use of the public addresses that IPv4 supports, NAT and PAT also help to hide the internal IP address structure from the public internet. Many bad guys operate and exist on the public internet, and I don't want them to have any vision at all on my private network, because the more they can identify or footprint or map out what my network infrastructure looks like behind that firewall, the more readily they can attack and target inside that firewall. So I don't want them to have any vision whatsoever. I'd like that to be a black hole. Well, that's one of the things that Nat and Pat help me do, is the bad guys on the public internet that might be able to capture packets, called sniffing on the public internet. They'll only be able to identify public addresses because NAT replaces private addresses with public addresses. And as a result, on the public internet, the only thing the bad guys will ever see are public addresses. And he has then no vision as to where is my DNS server on my private network? Where are my other servers? Where are my clients? What is the IP address architecture like in my environment? And so I hide all this from the public internet. So that's one of the benefits of using NAT and PAT on that external firewall as we've described. And some people talk about NAT and PAT as if they're two completely different things. And there is enough difference where they are different. That's why they have two different names. But at the same time, if I plan to implement NAT, I can't really do it effectively unless I also use PAT. So consider that if you have NAT, you're also running PAT. They operate like Siamese twins. You simply cannot separate them if you need the functionality, full-blown functionality that they support. So what we can use NAT and PAT for is use one public IP address and share that one address amongst dozens or hundreds or even perhaps a few thousand users on the private network. Many clients can share one IP address, public IP address, for use on the public internet for browsing purposes. We also can use something called port forwarding. Again, this is a combination of NAT and PAT, where I can use one public IP address, and using port numbers, I can steer an inbound packet to port 25 to a private IP address inside that hosts my email services. An inbound packet to port 80, I can use NAT and PAT to steer that to the web server on my private network. An inbound port 443 to my web server that's running SSL. An inbound port 21, map that to the server that's running my FTP server on my private network. So this is called port forwarding for inbound services, providing public services to the internet where the request is anonymous. And then on the next one, we have a one-to-one mapping. So suppose I have an application server that is stateful. In other words, it has to maintain session state for each client that is using the application. Typically what they do there is the application server will live on the DMZ, and you have these telecommuters that live out on the internet using public addresses. They will connect to your firewall using a public IP address, but to the one port for the application server. This would be the primary port for the application server. Let's pick a number of 20,000. So inbound to port 20,000 on a public IP address. And that will connect to that application server. But once the user authenticates on that application server, the application server will redirect them and say, the next time you communicate with me, you use port 31,200. And that way I'll know it's you, Bobo. And that way I can track your session and identify where you are in the process in my application. Maintain stateful information about your session. So the application server will now redirect each client from the authentication port to the session port for each individual session, so they can maintain different session state data for each connection. So in this case, I'll need to do a one-to-one mapping. I'll take one public IP address and map it to the IP address on the private side for the application server. And now it doesn't matter what port number it is inbound. all those inbounds to this one public IP address gets mapped to the one server, the application server, on the private IP address space. So this has been a look at network address translation NAT, and its very close relative, perhaps even Siamese twin, port address translation PAT. We'll take a break here and we'll pick up where we left off.